In this video, we're going to talk a little more about chemical formulas, what they mean, and how we determine them. So let's think about a formula. MgCl2, for example. What does that mean? It means that for every one atom of magnesium, I have 2 atoms of chlorine. It also means, since 6.02 times 10 to the 23rd is the number of atoms in a mole every time, that for every 1 mole of magnesium, I have 2 moles of Cl. And that's true of every single chemical formula. The subscripts tell you a mole-to-mole ratio. Now remember, that doesn't mean that in your beaker of magnesium chloride you have only 1 mole of magnesium and only 2 moles of Cl. You have lots and lots and lots of that, but that's the lowest ratio. Ionic formulas, ionic compounds, remember, always have lowest ratio. The lowest ratio formula is called the empirical formula. Okay? The empirical formula is the formula that shows the lowest ratio between the elements in the compound. Now, as I say, ionic things are always empirical formulas. But molecular things, things that are bonded with covalent bonds, not always the empirical formula. For example, let's take a look at these 2 organic compounds. This guy here has 2 carbons and 4 hydrogens. That's C2H4. This guy here, 4 carbons, 5, 6, 7, 8 hydrogens. Both of these are perfectly valid organic compounds. They exist. They have totally different properties. They have different names. This one would be called ethene. This one would be called a butene. But notice their formulas. This guy, C2H4, this guy, C4H8. Both of them, if you reduced it to the lowest terms, would be CH2. Alright, 2/4 is really 1/2. 4/8 is also 1/2. Both of these have a 1:2 ratio. This CH2 here is the empirical formula. These things that are not the lowest ratio are called molecular formulas. Now, molecular formulas are very important when it comes to organic, to covalent things, because CH4 is not what either of these things are. The molecular formula is what the actual compound is, the reality of the compound. Organic things cannot be reduced to a lowest ratio and still have it be meaningful, whereas ionic things are always lowest ratio. Now, let's think math. We're going to start with empirical because it's easier to think about. Let's stick, for example, with MgCl2. If I say to you, what is the percent composition of MgCl2? That means what percent of any sample of MgCl2 is Mg, and what percent is Cl2. And I mean that by mass, a percent by mass. Not a percent by moles, but a percent by mass. Okay, this is actually the easiest problem you will ever do in chemistry. Because what is percent? Percent is the part over the whole times 100. That equals percent. So that's exactly what we're going to do here. We look on the periodic table, and we see that the molar mass of Mg is 24.31 grams per mole. And Cl is 35.45 grams per mole. There's two of these. So we calculate the molar mass of MgCl2 is 95.21 grams per mole. That is the whole. And each of these guys are the parts. 24.31 over 95.21 times 100 is 25.53%. This guy, the chlorine, 35.45 times 2 is 70.90. So 70.90 over 95.21 times 100 equals 74.47%, which, by the way, it darn well better add up to 100%. Because that's all there is in the compound, Mg and Cl2. So my percents always add up to 100%. Always. That's one way to check and make sure you're right. Or to save you a little work. Once you figured out that was 25.53, this one had to be 74.47. So that's percent composition. It's 25.53% magnesium and 74.47% chlorine. Now, to find an empirical formula from these percents, we could do exactly the same thing, but backwards. So that's what we're going to do. In an empirical formula problem, you're given percents or you're given grams. It doesn't actually matter which one you're given. And you're asked to find the empirical formula. So, let's take these percents that we just found and go backwards and go back to the empirical formula. 25.53% magnesium. So we know we have a compound that is 25.53% magnesium and 74.47% chloride. Okay. The thing about percents is it doesn't matter how much of the compound I have. It's always going to be that same percent. So that's a good thing. We're going to assume 100 grams. Why are we doing that? Because it makes our lives easy. 25.53% of 100 grams is 25.53 grams. We could have assumed anything. But hey, that's the one that makes our lives easy, so that's what we're going to go with. Now, an empirical formula is a ratio of moles. So we're going to take these grams and we're going to turn them into moles. So the molar mass of Mg is 24.31 grams. So we're doing simple gram to mole conversion. 25.53 divided by 24.31 gives me 1.050 moles. Now this one, again, we're assuming 100 grams, so 74.47 grams of Cl. There's 35.45 grams of Cl in 1 mole of Cl. Again, I do the math, and I get 2.101 moles of Cl. Now, I'm kind of done in the sense that these are mole-to-mole ratios. For every 2.101 moles of Cl, there's 1.050 moles of Mg. But of course, we don't really want formulas with weird numbers. We want formulas with whole numbers. So what we're going to do to get whole numbers is we're going to divide. We're going to divide by whichever one of these guys is smaller, just so we guarantee one of them's 1. And nothing's lower than 1. Okay, so I'm dividing both. Remember, in math, I can do anything I want as long as I do it to have both things. I'm going to divide by the smaller one. This guy is clearly 1. 2.101 divided by 1.050 is, in fact, 2. And oh, look, I get my MgCl2 formula back. 1 to 2 ratio. And that's exactly right. Now, little word of warning here. You cannot round. You'll notice this really is exactly 1.00000. This one, when you do the division, is 2.0000. Do not round. If you get something like 1.8 when you do the division, don't round up to 2. It probably means you did something wrong in your math. But it might be that there is no 1 in the formula. You'll notice when you're doing this, you're rigging it, so something's a 1. But what if you have a formula that's something like Al2S3? And that's the one you're trying to find. When you do the division, I don't want to do this all out because it will take a long time. But what's going to happen is you're going to have some grams of Al that you've turned into moles. And it's going to end up being something like 1.333 grams. And then this one, you have some grams of sulfur. And that one's going to end up being something like 2.00 grams. And then you're going to go, oh, let me divide by the lowest, 1.333, 1.333. This guy ends up being 1, but this guy ends up being 1.5. And you can't round that. You'll actually get the wrong formula. What you say to yourself is you say, oh, that guy, that's a half. And I know to get a whole number, I have to multiply it by 2. Now, again, math says I can do anything I want as long as I do it to both things. So I multiply both of these by 2, and I get a ratio of 2 to 3, which is exactly what I wanted. Okay, so if the formula is going to come out to be something like this, where there is no 1 in the formula, you will not get whole numbers up and down the board here, and you have to multiply by something to get whole numbers. So look for that. If something comes out to be 1.5, you're multiplying everything by 2. Look for the common fractions. Remember, 1/2 is going to come out to be 0.5. 1/3 is going to come out to be 0.333. 1/4 is 0.25. Things like that. Look for those as your decimals. If it's something that's not a whole number and not a common fraction, double check your math. That's probably where you've made your mistake. Now, molecular formulas. If you're trying to determine a molecular formula, you need 2 things. 2 things have to be given to you. Okay? You need an empirical formula, and sometimes they ask you to find that, but that's okay, you can do that. But you need an empirical formula or some way to find it, and you need a molar mass. You need a molar mass. We think back to these examples that I gave you before. Both of these have the same empirical formula, but they have different molar masses. That's how you're going to tell what molecular formula you're looking for from an empirical formula. Let's say, for example, you have that empirical formula of CH2. Okay, that's your empirical formula, your lowest ratio formula. and I tell you that the molar mass of the thing you're looking for is 56.12 grams per mole. Okay, here's what you do. The first thing you want to do is find the molar mass of the empirical formula. So CH2 is the empirical formula. You say, oh, carbon, that's 12.01. Hydrogen, that's 1.01. But there's two of them, so that's 2.02. So 12.01 plus 2.02 is 14.03 grams per mole. That's the molar mass of the empirical formula. So then you say to yourself, this guy is the molar mass of the compound I want, the molecular formula. This guy has to be a multiple of this guy. So in order to find what multiple that is, I divide. 56.12 divided by 14.03. I plug that into my calculator, though really I could probably do that in my head. And I get, oh look, a whole number, and that whole number is 4. What that means is the molecular formula I'm looking for is 4 times the empirical formula. Now this one will always be a whole number. It's never going to be that 0.5 thing or anything like that. That's got to be a whole number. So 4 times CH2 is C4H8. And that is my molecular formula. One more thing we've got to talk about, which is hydrates. Very, very similar. Same ideas, which is why I'm throwing this in here. A hydrate, you might have seen those in the naming chapter just a little bit. Let me give you an example of a hydrate. CuSO4.5H2O. Okay. See this guy, this dot? That dot does not mean multiplication. Not like in math class. That dot means that this water is loosely bonded to the CuSO4. You know how in the summer you have like Kool-Aid or any kind of powder, sugar, anything like that, that gets wet and clumpy? It's gathering moisture from the air. That's the whole idea of these things. The water is kind of loosely bonded into this crystal structure, but in a known ratio. This 5 here says to you that for every 1 mole of CuSO4, I have 5 moles of water. Okay? For every 1 mole of CuSO4, I have 5 moles of water. In that sense, it's very much like another element with a subscript. Okay? Only it's water and it's loosely bonded. If you're figuring out the molar mass of this whole thing, it's 1 copper, 1 sulfur, 4 oxygens, 10 hydrogens, and another 5 oxygens. Add them. Remember, that's not multiplication. Add them up. But this 5 is distributed. There are 10 hydrogens here and 5 oxygens over here to go with the 4 oxygens over there. Now, the problems that are involved in hydrates are exactly the same as the ones we just talked about. You can find a percent of this. You can find what percent is water. You could find what percent is the anhydrous, which is this part without the water. You could find the empirical formula. Only just treat water as a whole. Don't talk about hydrogens and oxygens, but treat water as the whole. In a laboratory, if you heat up the hydrate, you will actually drive the water away. CuSO4.5H2O. That triangle means heat. So when you heat it up, you actually drive the water away, and you end up with solid CuSO4 and gaseous water. We will do some hydrate problems in class, don't worry. But really, they're just a variation on the theme we've already talked about. That's all you need to know.